Here in session 113, which is our final session, we're going to look at infinite geometric sequences. And the infinite geometric sequences that we're going to focus on here is a geometric sequence in which the numbers, each successive term, is getting smaller and smaller and eventually approaches the number 0. Well, here we have an infinite geometric sequence. Our first term, t1, is 80. Our second term, t2, is 8. Next, 0.8, 0.08, 0.008, 0.0008. And then the 3 dots means that that particular sequence continues on indefinitely. Let's take a look at our first term here. If you remember, a geometric sequence is a number sequence in which you have to multiply each term by the same number in order to reach the next term in the particular sequence. Well, at first thought you might say, well, we didn't multiply anything by the 80 to get 8. We divided. We divided by 10. Well, you're right. 80 divided by 10 is 8. But if you remember in algebra, division is the same thing as multiplying by the inverse of that particular number, the reciprocal of that number. 80 divided by 10 giving us 8 is the same thing as 80 times the reciprocal of 10. Well, what's the reciprocal of 10? 1/10, or 0.1. 80 times 1/10 equals 8, or 80 times 0.1 equals 8. So we can see here that we are in fact multiplying each term by 0.1, or 1/10, to give us our next term. 8 times a tenth is 0.1, or 0.8. 8 times a tenth is 0.08. 0.08 times a tenth is 0.008, and 0.008 times a tenth is 0.0008, and so on. So let's go ahead and take a look here and see if we can see if the sum of each of these numbers added together will just approach a particular number, or whether it will increase indefinitely itself as well. Well, if you remember, when we had a geometric sequence where each term was getting bigger and bigger, the sum of those terms approaches infinity. There's no limit to it. And the reason why is each number in the term keeps getting bigger and bigger. In this particular geometric sequence, each term is getting smaller and smaller. So let's see if we can detect a pattern. If we were to continue on this sequence just beyond the 6 terms that we had, let's say we took it out to 50 terms or 600 terms, would all of these terms added together approach a specific number? Well, we can see that it in fact will. And let's see if we can just take these first 6 and determine what that'll be. We're going to take our first term, which is 80, and we're going to add our second term to it, which is 8. And I'm going to go ahead and put a decimal point here after each of those. And we're going to add to it our third term, which is 0.8, and add to it our fourth term, which is 0.08, our fifth term, which is 0.008, and we're going to add to it our sixth term, which is 0.0008. So let's add all these together and see what we get. Well, we need to go ahead and visually, it may help you to do this, go ahead and add 4 zeros after that so that each of the numbers, this one will add 4, so that each of our numbers has 4 decimal places to the right. Here we're going to add 3 zeros. That'll get us out to our 4th point, or our 4th place, 2 here, and 1 there. If we take our columns now and add them up, all those zeros plus the 8 will give us an 8. All those zeros plus that 8 is going to give us another 8. Same in this column, all zeros plus 1 8. All zeros plus 1 8. Put a decimal point here. 0 plus 8 is 8. And in our tens place, 8 plus nothing else is 8. So we can see here that all of our first 6 terms combined together produce a sum of 88.8888. Well, if I were to go ahead and add a 7th term, which would be 0.0008, 4 zeros with 1 8 after it. And if I were to add that to this, what would it produce? It would produce an extra 8 here at the end. And if I produced an 8th term and added it here, what would it do? It would add another 8 to this end of it. And it would continue on indefinitely. So what conclusion do you think that you can make? Which number does the sum of these terms approach as we get closer and closer to 0? What it approaches is 88.88888 indefinitely. And so another way of writing that is just simply 88.8 with a line over it. And remember, that line means that whatever's underneath that line repeats indefinitely forever. So we can see that the sum of this infinite geometric sequence approaches 88.8 with a line over it as our terms get closer and closer to 0. There's also a formula that will produce the same result for us. Many of our geometric sequences are not as simple as what we had on the previous screen, and they're much more difficult to calculate out sometimes. So let's take a look at our formula that we had from a few sessions ago. The sum of the first n terms of a geometric sequence is going to be equal to your first term, which is t1, times r to the n minus 1. And remember, r is the rate that you're multiplying by each term to get the next term. So our rate over here is going to be 1/10, or 0.1. So t1 times r to the n minus 1 over r minus 1. Well, if we go ahead and use our distributive property, take our t1 and distribute it through, let's see what we get. T1 times r to the n is going to be t1 r to the n, and then t1 times a minus 1 is going to be a minus t1. Then we're going to write that over the r minus 1 again. So we've rewritten our first equation here now as our second one, and the only difference is that we used our distributive property. Now, as we saw on the previous screen, as each term got smaller and smaller, that when we took that term and multiplied it by our 0.1, which was our rate, that this number became very small. 0.08 was our fourth term. 0.008 was our fifth term. 0.0008 is our sixth term, and so on. So that you could see, if we were to approach, say, our 50th term, we would have a number that would be extremely small. And when you take that number that's extremely small, that number itself is getting very close to 0. So what if we were to take our t1 r to the n, and let's say for the moment, let's ignore that, because what we're trying to find out is what is the sum of the first n terms of this sequence going to approach as this component here, t1 r to the n, gets very close to 0. So we're going to ignore it, because very close to 0 is going to be, in essence, for us, 0. What are we left with then? If this is 0, s to the n would then equal minus t1 over r minus 1. So I've gone ahead and rewritten that down here in our third line. The sum of the first n terms is going to equal minus t1 over r minus 1. Well, I really don't want minus t1 on top. I want t1. So what I'm going to do is I'm going to multiply both the top and bottom here by minus 1. And remember, minus 1 divided by minus 1 is simply 1. And taking anything and multiplying it by 1 does not change the value of it, because anything times 1 is simply 1. So let's go ahead and multiply that through. What is minus 1 times minus t1? Well, that would be a plus t1, or simply t1. Let's take our denominator. Minus 1 times minus 1 is a positive 1. And then minus 1 times r would be minus r. So rewritten then, the sum of the first n terms as our number approaches 0, as our terms approach the number 0, is going to equal t1 over 1 minus r. Well, let's go ahead and use that formula and see what we get. Plug it in. S to the n is going to equal t1. Well, our first term is 80. That's what t1 is. And then we're going to divide that by 1 minus r. Well, what is r? What is the rate that we multiply each term by to get our next term? Well, our rate is 0.1, or 1/10. Well, what is 1 minus 0.1? Well, 1 minus 0.1 is just simply 0.9. So I'm going to erase this and just rewrite 0.9, which is the same thing as 9/10. let's come down here and divide it out. Top divided by bottom. You have 80 divided by 0.9. And we're going to move our decimal place in our divisor here over 1. So that means we need to add an extra 0 here and then insert our decimal point. So our decimal point is now gone from before the 9, and it's now after the 9 in our divisor. Well, let's go ahead and divide. 8 times 9 is 72. 80 minus 72 is 8. We bring down the 0. 9 goes in 80, 8 times. 8 times 9 is 72. 80 minus 72 is 8. You ought to be able to see the pattern of what's going on here. We're always going to be having an 8 up here times the 9. That'll give us a 72, and when we subtract it from the 80, that's going to give us 8 once again. We then bring down the 0. That's going to give us 80. We're in an endless cycle. We are always going to have an 8 up here, continuing on indefinitely. And as you remember from the previous screen, the number that we got was in fact 88.8888, and the 8's continued on indefinitely. So if we were to rewrite this using a shortened version, we're going to see that 88.8888 is simply 88.8 with a line over it. So this formula here was able to show us that as this sum approaches 0, that the number, the sum itself, will approach 88.8 with a line over it. First example here, we just took 6 terms, saw the pattern, saw that it approached 88.8 with a line over it. The second one, we used a formula. This formula is very helpful for many sequences, like I said, that are more difficult than the ones that we just looked at. Okay then, quickly as a review, if you have an infinite geometric sequence in which the terms are getting smaller and smaller, the sum of the terms in that sequence will approach a very specific number. And that number is calculated by the following formula. The sum of the first n terms is going to equal T1 over 1 minus r. Okay, that not only wraps up session 113, but it also finishes up elementary algebra.